All right, well, good morning. Welcome to our last Monday in February. Um, we're moving right along, right? After this week, there's just a few more weeks left. So today's plan, obviously, we'll go ahead and go over homeworks and stuff like that. But then I want to show you, again, just real quick, some exponential decay. We'll just do an example of an exponential decay, just to kind of round up our discussion from last time. And then I'm going to introduce you to some new functions and what their derivatives and integrals look like. And they are called the hyperbolic trig functions. Oh, yes, hyperbolic trig functions. So anyway, that's my plan. But let me start with you guys. What do you want to see from the homework? I'm sure there are probably a few out there that you'd like to look at. All right, so from 2.7, numbers 6 and 8. Okay, and then number 9 from 2.6, the Pappus formula. Now I know I didn't show you Pappus's formula because it's Pappus's formula. It's pretty straightforward. And then from 2.8, 25, 27, 28. This list is officially too long now. We'll still kind of look at them, but I won't probably go through all of these. Okay, so let me go ahead and share my screen and we will go take a look at those. All right. Let's just see what the exponential growth and decay guys are. That Lexi asked for. So let's see, 25, 27, and 28. Okay, so let's look at this one. So the city of Anvil. Okay, you just weren't sure how to set equal. Okay, so let's see what we can do here. So the city of Anvil is currently home to 23,000 people, and population has been growing at a continuous rate of 5% per year. The city of Brinker is currently home to 18,000 people, and the population has been growing at a continuous rate of 6% per year. In how many years will the populations of the towns be equal? All right, so let me switch to a whiteboard here real quick. And let's see if we can answer this. All right. So basically, we've got two different functions going on here. I'm going to call them A and B. I think that's probably why we were told they were Anvil and Brinkerton or whatever. So, so we got A is equal to. Now, they told us some stuff about it. They said that it's currently home to 23,000 people and it's increasing at a rate of 5% per year. So our initial amount is 2,300 and we're growing at a rate of 5% per year. All right, and so then for Brinker, they said it was 18,000 at 6% per year. All right, and so we want to find out when are these two populations going to be the same. So we'll just take those two equations and we will set them equal to each other. So we got 23,000 e to the 0.05t equals 18,000 e to the 0.06t. So then, Alexi, when you put in the chat box, you said you just didn't know how to set equal. I'm thinking it's probably not this step. I'm guessing you probably knew how to do that. It's more the where do we go from here? Yeah, okay. Well, I'm going to do what we always try to do, which is get all the t's together on one side and everything that's not t on the other side. So I'm going to start by moving this e to the 0.05t over to the right. Why I'm going to the right, just because I can see what's going to happen here. And so I'm going to do this by dividing, because right now it's being multiplied, right? So if I do that, I have 23,000 equals 18,000. And then this bit, since I'm dividing with exponents, then I end up subtracting the exponents. So I have 0.06 minus 0.05. I dropped a 0 on that. Sorry about that. 0.05 t. So 0.06 minus 0.05 is 0.01. Goodness. Decimal issues today. Okay, so now I'll divide the 18,000. Let's move those guys over. And what that leaves me with is 23/18 is equal to e to the 0.01t. And now it's take a log and so on. All right, so is that a good enough shove for number 25? Because then it's just a couple more steps. All right, so there's that guy. So let's real quick see what numbers 27 and 28 look like over here. All right, so 27. Find the time it takes for 8,600 to double when invested at an annual interest rate of 18% compounded continuously. All right. So this one, let's just set it up real quick. So we're starting with 8,600. We want to double it. Okay, well, let's go to the whiteboard here. So we're going to use the good old A equals PE to the RT. We're starting with 8,600. We're at an interest rate of 18%. And we want to double it. So we want to see how long it takes until it's twice as much.
Just really quickly, Bruce, it wasn't like that. Like there's like a ton of these problems in this homework set, and it's just this one that's like, I don't know if it's like a decimal or if you could maybe just look at mine after.
Okay, I'll do that. We can look at it after. Let me just real quick do. If we divide by the 8,600, we get 2. And when you do this, you end up taking a natural log. And the reason I wanted to show this is if you do doubling time, it's always the natural log of 2 divided by your interest rate. Just always. I don't think I mentioned this last time because I figured it would come up on a homework. But doubling time is always natural log of 2 over r. Always. Just like half-life, if you were to look at that for a decay problem, half-life is the natural log of 1/2 divided by, I'm going to put k because that's usually what we see for half-life, where k is your growth or your decay rate. So it could very well that there's a programming issue with 27, but this is the general process. Okay. So remind me at the end of class, and we'll take a look at that, Alexi, because I'm sure I will forget by that point. Okay, so then let's look at 28. All right, so 28. All right, so we've got some money that's being invested, 7% per year. Find the value of the investment at the end of 5 years if the interest is compounded annually, semi-annually, monthly, daily, or continuously. Okay, so for this one, we have two different formulas. This guy with the p times 1 plus r over n to the nt, that's for the non-continuous. So that's for all the other ones. The p is still the same. It's the initial amount being invested. R is still your interest rate, and t is still your time. So for every single one of these problems, R is going to be 0.07 and t is going to be 5. For mine, right? Obviously, you might have a different interest rate and time. And then the principal, the p is always going to be the 27.7. The n is how many times you compound your interest each year. So for annually, n is going to equal 1. Semi-annually, n is 2. Monthly, n is 12. Daily, n is 365. So for each of these, it's just a matter of plugging the values in. Make sure you round to the nearest penny. I wouldn't round until the very, very end. I would just put everything into my calculator and then hit enter, and then round at that point. So let me just show you one of them, and then we can probably call it good. So let's say we were looking at the monthly. Okay, so and I don't remember what the numbers are, so we'll just do whatever. But let's say we're doing 17,000 at 7% monthly for 5 years. Okay, so the P is going to be 17,700. The R is 0.07. If we're doing it monthly, that's going to be divided by 12. And then we're going to have 12 times 5. So, yeah, this is just plug and chug now. All right, and so the only thing that's going to change is your n value, depending upon how often you're computing. All right, cool. So we just banged out those guys from 2.8. So let's keep going back in time. Let's go to 2.7. And I saw 6 and 8 were on our list here. So let's see what those are bringing us. All right, so this one, evaluate the definite integral. We've got 8 over x natural log of 7x. All right, that one looks fun. Looking at that, substitution is probably going to be our best guess. So let's try it. All right, so we had the integral of 8 over x natural log of x. Oh, not natural log of x, natural log of 7x dx. All right, so there's some kind of obvious things to try to substitute for, and let's kind of go in order. The first thing you might try is just u equals 7x, because then we get the natural log of u. Another choice would be to do u equals natural log of 7x, because then we've got 8 over u and some other stuff that we might have to substitute. And a third possible choice could be the x natural log of 7x, right? The whole thing on the bottom, because then we just have u. So I would say that those are probably the most likely choices for you. Turns out the one we're going to want to use is this guy. So you might be asking yourself, how the hell does Bruce know that? Just by looking at it, how does he know that's going to be the one? Well, I mean, there's I've done this a billion times, but what it really is I do the derivatives of these things and I think about what's going to show up, right? Like come back to the u equals 7x. Its derivative is just 7. That's not going to be very useful when it comes to substituting in and getting rid of the other stuff out here. So I think about this one, natural log of 7x. Well, its derivative is going to be a 1 over x, right? Or, well, a 1 over 7x times the derivative of 7x, right? But the key is I recognize because it's natural log, that's going to give me an x on the bottom. And I look over here and I see this x on the bottom and I go, oh, that's going to be good. That's going to end up being part of my du and it's going to go away. And then if I look at u, I recognize I got x times natural log of 7x, which means I'm going to need the product rule. And I'm all about not doing the product rule. That's just going to be a horrible looking derivative. All right, so that's the thought process. That's what goes through my head when I'm thinking about what u to do. I'm doing one more step in my mind. I'm trying to anticipate what the derivative is going to look like to see if it's part of this function. All right, well, so I'm going to use this. So then u prime, remember with natural logs, we get whatever's on the bottom, or on the inside on the bottom, and then we take the derivative of what's inside and put it on top. Well, the derivative of 7x is 7. So we get du is equal to dx over x, which is exactly that stuff. So when I go and I do this substitution, I'm going to have over here the integral of 8 over u du. Right? The natural log of 7x, that was my u. The dx over x became my du, and the 8 is just there. So integrating this gives me 8 natural logs of u. Let's see. And so I can substitute back in. Oh boy, we have a nested log. How beautiful is that? So we get 8 natural logs of the natural log of 7x plus c.
So I noticed for that, those couple of problems with the natural log and everything that it wouldn't give me the points unless I put absolute value in there as well.
Yep, because technically there do need to be absolute values here. And I know that I know I'm sloppy about that. I know that when I show you things, I don't tend to put the absolute values on that. And honestly, I'll just tell you that that's because of two things. One, I'm lazy. We'll call it as it is. But also because of my background as a science guy, that never matters when you're applying this to the real world, because whatever your real life scenario is, it's going to be such that these things are defined. And so they're going to be positive, but technically, yes, they do need to be absolute values. So anyway, so I apologize if my being lazy has led to you guys being lazy and forgetting about it as well. But technically, yes, when you integrate with the natural log, you need absolute values. All right, so better for that one, I hope, number 6. So let's go take a look at number 8. See what that one's got to show for us. Okay, so more of the same. Same kind of idea. Let me just write this down. X squared natural of x. Going from 1 to e to the 9. All right. So the only real difference with this one is we have bounds. I mean, yes, it's a different integral, but it's really the same kind of structure. So we have 1 e to the 9 dx over x square root of natural log of x. All right, so again, you think about some choices for your u substitution. One would just be natural log of x. Another option might be the square root of the natural log of x. A third, and definitely not going to be my option, is going to be x times the square root of natural log of x. So basically, I'm just sort of like peeling this thing apart and the different layers. So again, think about what the derivatives look like. The derivative of natural log is going to be a 1 over x. And that should immediately make you go, oh, that's the one I want, because I've got a 1 over x here in my integral. So forget about these two. Those are going to be horribly nasty. Let's use this one. So then du is going to be 1 over x dx, which changes this into 1 over square root of u times du. All right, now I'm actually going to go ahead and change the bounds at the same time. Let's plug these things in for x. So my bounds, if x is e to the 9, the natural log of e to the 9 is 9. And if I plug in 1, the natural log of 1 is 0. All right, so that's u to the minus 1/2. So when I differentiate that, I get 2 times u to the 1/2, plugging in 0 and 9. So that's 2 square roots of 9 minus 2 square roots of 0, which to me looks like 6. I'm a big fan of just changing the bounds while I'm doing my u substitution. But if you would prefer, you can turn this back into x's with the original bounds. You'll end up with the same value. And this is a good example of what I was just talking about with the absolute value stuff. In this situation, you'll notice that the natural log is always positive between 1 and e to the 9. So even if we were to integrate, we don't have to worry about this thing being needing an absolute value and all that. So just FYI. Basically, I have to convince you that it's okay that I've mostly been lazy this whole time. Anyway. All right, so are we better there for the bits with natural logs and all that? Specifically, I'm looking at you, Chase, since you were the one who asked about them. All right, so lastly, let's go back and find that one with the theorem of Pappus. All right, so let me switch screens here. Oops, hold on a second. Too many windows. Okay. That just made me laugh. I was on a meeting with actually the president of the college, and he got into one of those and was like, crap, too many windows. I'm like, oh, I feel your pain, man. I feel your pain. Okay, so that was number 9 from 2.6. Okay, So use the theorem of Pappus to find the volume of a torus. Torus is just a donut. Assume that the disk of radius a equals 1 is positioned with the left end of the circle at x equals b equals 8. And we're rotating it about the y-axis. Okay, let me write that down real quick. So that's 8. This is radius 1. Okay, cool. So let me jump back to whiteboard. So I didn't show you guys the theorem of Pappus, okay? And that actually was intentional because I figured it was something you could probably grab pretty easily from the text. So for those of you who kind of got it from the reading and all that, how's the theorem of Pappus work? Okay, so maybe that's the issue. Maybe I should have shown you the theorem of Pappus.
Yeah, so I was just like, I tried just like plugging in the numbers to the formula a couple of times, and I always like it just like wouldn't accept that. I was putting in like pi squared, and didn't like that, and I tried just doing like decimals, and it was like no. So I was just wondering if maybe I was failing to set this up correctly. That's, so I'd like to see just how you set up the problem.
Okay. So the deal with the theorem of Pappus for finding volumes is you just need to know how the centroid has moved. So yeah, you're going to look for what we're doing when we have the theorem of Pappus is we're taking some sort of a region in the plane. In this case, it's a circle, but in general, you're going to take some region of the plane and you're going to rotate that around an axis to create a shape, right? So we're taking a circle, rotating it around to make a donut, but you can imagine we could take a square and rotate that around and get whatever the funky weird shape that would be or whatever. All right. Now, to use the theorem of Pappus, what you need to know is where the center of mass is, or the centroid. All right. Because what you're going to do is you're going to take the area, the cross-sectional area. So for us, it's the circle. And you're going to multiply that by how far the centroid moved. So basically the circumference of the circle that the centroid traveled on. Okay, so that's the idea with the theorem of Pappus. So let's go ahead and kind of get this thing set up. So we've got our circle. That's got a radius of 1. So let's get its area first, right? So its area is good old pi r squared, which is going to be pi. Okay, so now what we need to do is we need to multiply this by the path of the circle. So I'm just going to put here the path, the length of the path for the center of mass. So the centroid of the circle is easy because it's going to be right smack dab in the middle. And so what we need to know is how far away is it from the axis of rotation, because that's going to create our circle here. Pretend that that's a circle, just kind of looking through it, right? And we need to figure out what is this path. All right, well, so that's a circle, and the circumference of a circle, I'm going to call it 2 pi big R, because it's a different R. So the question is, where is that? Well, we were told that the left side of the circle was 8 units away. So right there. So what's that make big R? All right, so Rigney just said it's 9. Good. Yeah, it's going to be 9 because it was 8 to the side and then another 1 for the inside. So it's going to be 2 pi times 9 or 18 pi. Okay, so we'll put that in there. So putting that all together, oops, the volume then is 18 pi squared. All right, so let's go put that in here. All right, so it says write as an exact expression. Okay, so we're gonna have 18. Why is my, oh, there we go. Because my number lock is off, 18. And then we're gonna to have pi squared. So pi squared. I think that should be good. Yay. 1 out of 1. All right, so I don't know maybe what the issue was for that one, like because you were saying that it was like you were having trouble typing it in or something. So I don't know if it was a formatting issue. It could have been, yeah, I'm not really sure. Maybe were you squaring the 18 as well? Okay. As long as you were doing this process, Rigney, as long as you're doing that process, I think you should feel good about it. And it probably is just you hit something in wrong. So, all right. So cool for that one. All right. So a little bit of lots of things on there, but that's always good review. All right. So like I said, I just want to go ahead and show you an example of a exponential decay kind of problem, and then introduce you to some other functions. Actually, check that. I'm not going to show you exponential decay. You know how to do it. It's just a negative growth rate instead of a positive. I think it's better if we actually move on to these new things, because these functions you may not have ever seen up to this point, and I definitely want you to see them. So, because they're going to be kind of important going forward. So let me hop up to the whiteboard and I'll introduce you or refresh your memory on hyperbolic trig functions. All right. So there's another group of functions that you might have seen, you might not have seen, depending upon where you came up through the sequence. And these are called the hyperbolic trig functions. Sometimes you'll just hear them called the hyperbolic function, but they're the hyperbolic trig function. Now, where they come from is, well, all right. So you remember the trig functions, little sine, cosine, tangent. And if I were to ask you where those come from, most likely you're going to tell me they're ratios of sides of a triangle, right? SOHCAHTOA kind of thing. Opposite over hypotenuse, adjacent over hypotenuse. But some of you might go, oh, they come from the unit circle. Yeah, I know nobody's going to say that, but that's the dream up in here, by the way, is that you all think that. But the trig functions come from the unit circle, right? We look at the coordinates of the unit circle for the various angles, and whatever those coordinates are, the y gave us the sine, the x gave us the cosine, right? Well, hyperbolic trig functions are actually defined exactly the same way, except using the coordinates on a hyperbola instead of a circle. So basically, if you were to have, here's our axes, think about a unit hyperbola. Yeah, right. Basically, this one, this is the equation x squared minus y squared equals 1. So instead of x squared plus y squared for the circle, you do x squared minus y squared. If you were to do that, and then you were to take an angle and look at where it intersects, right? So this guy right here, this has coordinates x and y. And whatever those coordinates are, we define two new trig functions, hyperbolic trig functions, that are sine with an h and cosine with an h. And these would be the x and y coordinates of that point. Okay, so this stands for hyperbolic sine and hyperbolic cosine. All right, so that's literally what these mean. So you can see, well, you can understand. I was going to say you can understand why, no, probably not. But it makes sense mathematically, call these things sine and cosine, if you're kind of doing it the same kind of approach, and throwing the h on it, say, well, because it's the sine of the hyperbola. Okay, that's the stretch, right? Why are we going to do all this trig stuff on a hyperbola instead of a unit circle? Well, that's mathematicians being mathematicians. Like, honestly, it's like, yeah, it's worked for a circle. I wonder what happens if we put it on a hyperbola. Next thing you know, we get all these functions that actually matter. Anyway, so that's where these things are coming from. There's also a hyperbolic tangent. Guess how you get that? That's pretty obvious. Tangent is sine over cosine, so hyperbolic tangent is hyperbolic sine over hyperbolic cosine. And there's going to be a hyperbolic secant and a hyperbolic cosecant and all. Okay, so all these things exist, and they all follow the same kind of structure as before. All right, but we have names for them. We don't say hyperbolic sine. We don't say hyperbolic cosecant because that's just too much. All right, so we actually do have nicknames for all of them. So let me go ahead and show those to you. Oh, and by the way, the whole hyperbola thing, don't worry about that. That's not, it doesn't matter for what we're going to be doing. It matters very much for how they get defined, but beyond that, don't worry about it. Okay, so here are your different trig functions. So your hyperbolic names. And I'm going to put here the name, like what we actually say, the words that we say. All right, so the first one, the hyperbolic sine, we call this cinch, as in you're cinching up your pants. Okay, so cinch. This one is exactly what it looks like. That's cosh. Hyperbolic tangent is tanch. Hyperbolic cotangent is coth. The hyperbolic secant is sech. Think fetch with an S. And then you've got your hyperbolic cosecant. Okay, it's cosec itch. Cosec. That's when you say bless you. This is my all-time favorite function, by the way, just because of its name. Cosec. All right, so we've got sinh, cosh, tanch, coth, sech, cosec. It's just faster than saying the hyperbolic tangent. Okay, so when you hear me say these things, this is what I'm going to say. All right, well, it turns out that these guys have all kinds of properties, all kinds of identities, just like the trig functions did. The basic ones are exactly what you would expect. All right, so for example, we've got that tanch is sinh over cosh. We've got the coth is cosh over sinh. We've got sech is 1 over cosh. And cosec is 1 over sinh. So if those look a little familiar, they should, because those are exactly the same ratios as we had for the regular trig functions. So what that means for us actually is that we don't really have to worry about a lot of the tanch and sech and things like that. Really, we need to know sinh and cosh. You know sinh and cosh, and you get the rest. Okay, so these are the equivalents of the like the reciprocal identities and stuff like that. But there are also identities that are similar to like the Pythagorean and whatnot, but they look slightly different. They're slightly different now because of the fact that these are hyperbolic trig functions. So you probably remember the Pythagorean identity. That's like the one identity that anybody remembers from trig. That's the good old sine squared plus cosine squared equals 1, right? Well, with the hyperbolics, it turns out it's slightly different. It's cosh squared minus sinh squared equals 1. So we put the squares in here, just like we do on sine and cosine. Okay, but this is the hyperbolic cosine squared minus the hyperbolic sine squared equals 1. So I know what you're thinking. What the? Okay. Well, this comes from the fact that it came from a hyperbola. Remember the equation for the hyperbola? It's a difference of squares equals 1 instead of, for the circle, the sum of squares. Well, that's what this is. This literally comes from the equation for that unit hyperbola. So we don't call these the Pythagorean identities anymore because they're not from the Pythagorean theorem, or they're not related to the Pythagorean theorem, but they play the same kind of role. You can develop the others by doing the same kind of trick that we did before of dividing by sinh squared or dividing by cosh squared. Like if you divide everything here by cosh squared, you're going to get 1 minus tanch squared equals sech squared. And similarly, if you divide everything by sinh, you get coth squared x minus 1 equals cosecant squared x. So these are the Pythagorean related ones. Really, you only have to remember this first one because you can develop all the rest from it. And just remember, this comes from the equation of a hyperbola. The equation of the hyperbola was x squared minus y squared equals 1. So that's what that thing is. Okay, so these functions were created. Like I said, this is just how mathematicians think and what they do. Hey, all this stuff works for a circle. What if we make it so that's hyperbola? Okay. I mean, think about it. That's how like I came about. You can't do the square root of negative 1. What if I can? Right. So we get all this kind of weird stuff that happen. But it turns out these are really, really useful. Really, really useful. And in fact, you can even define them all in terms of exponential functions. I'm not going to show you where this comes from, but I'm going to show it to you or give it to you. So it turns out that if you were to look at cosh, it's actually equal to e to the x plus e to the minus x over 2. That's how this thing is defined in terms of exponential functions. Turns out you can define regular trig functions in terms of exponential functions as well. We just don't usually do it. These we tend to do it. So this is cosh, and then sinh, very similar. It's just e to the x minus e to the minus x over 2. Obviously, all the rest of them are going to be defined in terms of these, right? So like sech is just this flipped over. So 2 over e to the x plus e to the minus x. Flip this over to get cosecant. You can get tanh by taking sinh over cosh, right? So you can get all the other ones in terms of exponentials as well. These are the two that you should know. Okay. And their forms are pretty easy. If you know one of them, you know the other. It's just a matter of remembering. If you were, say, to put these two into this identity, you'll see that you do get one, right? It all ties together. So what these things look like, if you were to draw a graph of them, we'll go ahead and draw them both on the same set of axes here. So what cosh looks like it looks something like this. It is not a parabola. It is not a hyperbola. It's its own thing. It does have some like limiting values. Like it's got asymptotes. It's got an exponential function. If this is e to the x over 2, that's what this function approaches as we get really, really big. If you look at this equation right here, the e to the minus x, as x gets big, that gets less and less and less. So this approaches e to the x over 2. Similarly, on the other side, it's going to approach e to the minus x over 2. For kind of the same reason, if we go to really small x's, then the e to the x disappears. So that's why it's not a parabola, it's not a hyperbola. It approaches exponentials as it goes further and further away. We do have a name for this shape. We call this a catenary. Catenary. So that's the actual name for that, right? Like a parabola is the shape for an x squared. Well, catenary is a shape for a cosh. And I think I may have mentioned, if I haven't, you guys, this is the shape you get, like if you look at a power line that's hanging between two poles, right? Or any kind of a chain, rope, anything that's being extended from one place to another. It always forms a catenary because of gravity, how it works. So think about that. All of a sudden, so we've got this guy cosh, which is a out of nowhere kind of function, right? And or like just randomly, ooh, let's use hyperbolas instead of circles. And yet it has immediate use. Immediate use. You want to model a cable that's hanging between, two ski lifts supports. Yeah, it follows a catenary. Hyperbolic cosine. All right, so that's what hyperbolic cosine looks like. And then hyperbolic sine, if you look at that one, notice that it does kind of the same thing. It's going to, when we go really far out, the e to the minus x drops out, so it's going to look like the same e to the x over 2. But on the other side, the e to the x cancels, it's going to look like negative e to the minus x over 2, so it's actually going to go downward. And so what we see with that one is something that looks like this. And again, I know you've seen a billion things that have this shape. It is not the tangent. It is not like a cubic function, or it's its own thing. It is approaching these exponential graphs on either side, but it looks like this one. All right, so that's what sinh looks like. All right, all the other ones have their own graphs and all that, but in general, this is cosh and sinh. So I just want to point out a couple things to you here that are kind of important when it comes to the calculus. Look, notice sinh is always increasing, always going up. So it doesn't have an extreme. Cosh does. It's got a minimum. And we would actually see that if you differentiated set equals 0, all that good stuff. But more importantly, notice that cosh is even and sinh is odd. With the symmetry, we actually had the same deal when we had sine and cosine. Sine was odd and cosine was even. But I bring this up because that definitely helps us with integrals, right? Hopefully you remember even and odd. Like if you got an odd function and you integrate from minus a to plus a, cancels out. You just get 0. If it's an even function, minus a to plus a, you can actually just double integrating 0 to a, right? So there are some shortcuts if you recognize they're even and odd. All right. So there's sinh and cosh, at least their graphs. All right, well, let's start talking derivatives, right? What are the derivatives of these things? Because we need to know those, so we can do integrals and yada, yada, yada. All right, well, I'm going to start just by differentiating cosh. And we're going to differentiate it using the exponential definition. All right, so we're going to do the derivative d dx of cosh. So if we go back to the definition in terms of exponentials, that's the derivative of e to the x plus e to the minus x over 2. But we can do this pretty easily. The 1/2 is a constant multiple. the derivative of e to the x is e to the x. The derivative of e to the minus x is going to be e to the minus x times the derivative of negative x, which is -1. So there's the derivative of cosh. But if you just peek over here, you'll see that that is just a good old sinh. So the derivative of cosh is sinh. The fact that the derivative of one of them gives you the other shouldn't surprise you. I mean, we saw that with the regular trig functions. But what's kind of interesting about this one is that there was no sign change. The derivative of cosh is just sinh. Okay, so then what about the derivative of sinh? And I know what you're thinking. Here's where the sign change is going to happen. Well, look at sinh. If you were to differentiate it, the 1/2 is going to stick around. E to the x, its derivative is e to the x. The minus e to the minus x, we're going to get a -1 from the chain rule, which is going to make that plus. So the derivative of sinh is actually just cosh. So these two functions are kind of cool. The derivative of one is the other. Just period. There's no sign change or anything. So let me start making a list here of the hyperbolic trig functions and what their derivatives are going to look like. So here's our function, f of x. A little bit more space than that. F of x, the f prime of x. So the derivative of sinh is cosh. The derivative of cosh is sinh. Believe it or not, that's good news. Because I want you to think back to sine and cosine and differentiating and integrating. How often did you make the mistake with the minus sign? How often did that come up that when you integrated, you went, wait, when I integrate sine, does that give me a negative cosine or a plus cosine? Right, that happens a lot. Now, I don't have to worry about it. What's the integral of cosh? Sinh. The integral of sinh cosh. Derivative of sinh cosh. Derivative of cosh sinh. This don't have to worry about signs at all. All right, so there are those. Now you can develop derivatives for the rest. And these come from the, well, basically the identities on them, right? If you were to look at the fact that tanh is sinh over cosh, use the quotient rule, simplify, yada, yada, yada. Right? I'm not going to do this to you. But it turns out the derivative of tanh is sech squared. And even though none of you are showing your video, I can still see your shocked face. You're not shocked face, right? If the derivative of sinh is cosh and cosh is sinh, well, of course, tanh's derivative is sech squared. It's the derivative of tangent with secant squared. All right, so anyone want to make a guess for what the derivative of coth is? Well, you can better believe it's going to have a cosecant squared. But it does turn out that it is negative, so it kind of follows the property of what we're used to with tanh. All right, and then sech and cosecant. Well, obviously secant was secant tangent, so this is going to be a sech tanh, and cosecant is going to be a cosecant coth. Turns out both of those are negative. So good news, bad news time. Good news. That pretty much follows the same pattern as what we're used to. Bad news, the signs are jacked up a bit. Right? Like it doesn't follow the patterns with the plus or minus signs that we're used to for trig functions. But that's because these are different guys. These are hyperbolics. All right, so this chart is going to be useful for differentiating and also for integrating when we've got those forms. But I'm going to be 100% honest with you, because you know I'm always about this. This stuff's not that important. And I know you're probably like, why did you just show us all this stuff? Okay, this stuff's not important. But what it is important are their inverses. Okay, because just like trig, we had inverse trig, we also have inverse hyperbolics. There's a cosh inverse. There's a tanh inverse. You have to define them appropriately. Just think about that graph of cosh. The catenary, it is not one-to-one, so you do have to put a restriction on it, just like you do with the regular trig functions. But once you do that, you can also create the inverse trig functions. And what's more important in terms of our life right now and what we've been doing is not not just the hyperbolic trig functions, but their inverses. And I'll show you why. So I'm going to give you another one now. Where are we going to put these? Because I want to derive it. I'm going to give you another chart. All right. So this one held the regular trig functions, or the regular hyperbolics. This next one is going to have the inverses. So I'm going to put little minus ones in here for the inverse trig functions. But we're going to do the same thing. We're going to make a list of the inverse trig functions. I need it to be bigger. I was trying to be lazy again, and it didn't really work out. Okay, so f of x. Prime. So the first one's going to be sinh inverse. They're all going to be fractions. Why I need these a little bit larger. So cosh inverse, tanh inverse, cosh inverse. We'll worry about sech and cosecant when we get there. Okay, so I want to get their derivatives. Well, let me show you how this is going to play out with sinh. So I'm looking at y equals sinh of x, or sinh inverse. So think of it, it is what it is. It's the function that goes backwards from sinh. Right? Sinh, you plug in a number, you get something out. Whatever that came out, you plug that into inverse sinh, you get where you started. Okay, so we got this guy. Now, what I'm going to want to do is differentiate it. But I'm going to do something first. I'm going to take a sinh of both sides. All right, so I'm just going to do sinh of that side and sinh of this side. So I've got sinh of y equals x. x, because sinh and inverse sinh cancel. All right, now it's this that I'm going to differentiate. Differentiate both sides of this with respect to x. So I'm doing implicit differentiation. Hopefully you remember that from Calc 1. So the derivative of sinh, we already saw is cosh. And then I need to multiply by y prime, implicit differentiation. The derivative of x, of course, is just 1. So if I solve this for y prime, I get y prime is equal to 1 over cosh of y. All right, so hopefully everybody's mostly okay with this. I know the whole sinh of sinh inverse and all that is probably not something that you're down with right now, but hopefully the calculus at least makes sense. Okay, well now we're going to do one more thing. I don't want cosh of y, right? I really don't. I want that in terms of x's and things like that. So here's what we're going to do. We're going to make use of the Pythagorean identity for sinh, the sinh and cosh. So you may recall that we had the cosh squared minus sinh squared equals 1. That came from the hyperbola. Well, I can solve that for cosh. And if I solve that for cosh, that gives me the square root of 1 plus sinh. Right, the subtraction I move over becomes an addition, 1 plus sinh squared, and then I take the square root. All right, now I know you're looking at that and going, now he's just doing algebra for the hell of it. I mean, dude loves identities, so of course he's doing. No, there's a reason. Let's check this out. I know what sinh of y is. If you come back just a couple lines, come back up here, you see sinh of y is equal to x. And so this ends up being a really nice looking derivative. The derivative of inverse sinh is 1 over the square root of 1 plus x squared. All right, so again, just I'm using this piece right here to substitute in for my sinh. Sinh of y is equal to x. So inverse sinh, its derivative is 1 over the square root of 1 plus x squared. All right, now maybe you're starting to see why this is going to matter. Think about integrating. If we were to get a form that looks like this, that we're asked to integrate, we now know it's going to give us sinh. And you've seen forms like that. Not quite exactly like that, but you've seen like the square root of 1 minus x squared. You've seen with the square root of x squared minus 1, and so remember the inverse regular trig functions. These are going to show up when we're trying to integrate other functions that are similar in form to those that led to inverse regular trig. So this is why we actually care about these, because of the forms we're going to get. Okay, so you could actually do all the rest of them in a similar way. Cosh, start with y equals inverse cosh. Cosh of y equals x, differentiate, blah, blah, blah. And this is what you find. For inverse cosh, its derivative is 1 over the square root of x squared minus 1. So we now have a rule for every sum or difference of squares in the square root. We've got these two, and then if it was reversed, 1 minus x squared in the square root, that was the inverse sign. All right, tanh. This one's beautiful. It's 1 over 1 minus x squared, which is very similar to inverse tangent. You remember what inverse tangent's derivative looked like? Or how it was related to this? Inverse tangent is one you should know, because it was 1 over 1 plus x squared. So it wasn't these two swapped, it was change the sign on one side. Yeah, so it was 1 over 1 plus x squared. Well, 1 over 1 minus x squared, that's inverse tanh. Sweet. All right, now this one's kind of crazy. Inverse coth, its derivative is exactly the same thing. Okay, so now this definitely you got to go, ooh, wait a minute. Well, we'll talk about this in a second. But yeah, so inverse tanh and inverse coth, yeah, are the same thing. So they can just put in the chat box, well, that just complicates integration. Like it wasn't already hard. Yeah, we'll talk about this one. Don't worry, it's a you get one or the other. You have to pay attention to something else. All right, well, so there's your inverse tanh in your inverse coth. So to finish this off, let me continue our chart up here because we've got to have inverse sech and inverse cosecant. All right, so we have sech inverse. Sech inverse is minus 1 over x times the square root of 1 minus x squared. And cosecant inverse is minus 1 over the absolute value of x times the square root of 1 plus x squared, obviously. All right, so these now round out our different things that we're going to be able to integrate, different forms that also came from the inverse regular trig functions. You can see all the similarities, right? In fact, most of them are just a sign change somewhere. We've got 1 minus x squared instead of 1 plus x squared, right? Or we've got these things swapped. Instead of 1 minus x squared, it's x squared minus 1. So basically, this just takes care of all kinds of other forms for us. All right, so before we do any of these, let me real quick address the fact that these are identical. One thing I didn't tell you is I didn't talk about the restrictions on the inverse hyperbolics, because it's not, this is the only place where it's actually going to matter. Everywhere else, we don't really care. Unlike the inverse trig functions, like knowing the, for example, tangents between minus pi over 2 and pi over 2, right? Like those mattered for lots of reasons. It turns out that with the restrictions, that's what leads to knowing which of these you do. You use inverse tanh if that x is between 1 and -1. All right, so this is going to be we need to know where we are and what we're doing. But if your x's are between plus and -1, you use inverse tanh. Otherwise, you're going to use inverse coth. And notice that those are all just either less than or greater than. There's no equal, because if x equals 1, clearly none of those works. You've got vertical asymptotes for both of those functions. So even though you go, well, shit, now we don't know what we're going to do, you kind of do. You know it's going to be either inverse tanh or inverse coth, depending upon where you are. If you don't know where you are, we default to inverse tanh. And what I mean by that is, like, if we're just finding an antiderivative, for example, if you want any antiderivative, just go to inverse tanh. Because inverse coth is related to inverse tanh, and you can always get there if you need it. So I'm just going to put a star here. Inverse tanh is the one to know for the 1 over 1 minus x squared form. All right, so there they are in all their glory. So let me show you how this plays out. Right. So for example, let's say we wanted to integrate 1 over the square root of x squared minus 4 dx. So you look at that, and you probably have some flashbacks to the inverse trig functions. This is kind of looks like that form, but it's not quite, right? Had it been the square root of 4 minus x squared, we have an inverse trig function for that. If there was an x square root of x squared minus 4, we have an inverse trig function for that. But this one, if you notice, looks very much like inverse cosh. The difference is that there's a 4 here instead of a 1. All right, so here's what we're going to have to do. We're going to have to change that 4 into a 1. So we're going to have to do a little bit of algebra to get us to a point where it matches the inverse cosh picture. All right, so here's what I'm going to do. I'm going to factor out that 4. So I'm going to factor out a 4 in here. So that I get x squared over 4 minus 1. So you've seen that kind of trick happen before. All right, well, that square root of 4, that's just a 2. Integral of 1 over 2 times the square root. And I'm going to write this as x over 2 squared minus 1, if you guys don't mind. All right, so this is where we are at this point. And now this is begging for a u substitution. We're going to let u equal x over 2. So then du is equal to dx over 2. So if I do that, this now becomes the integral of Well, the dx over 2 becomes a du. Du over the square root of u squared minus 1. Right, x over 2 is now a u. And the dx over 2 stuff became part of the du. And now this is exactly the form for inverse cosh. So this is going to be cosh inverse of u plus c. Well, I got to replace the u. So this ends up being cosh inverse of x over 2 plus c. So we started with this integral, and we found out it's antiderivative. And if this had bounds, right, if we had the good old integrate this from 10 to 12, okay, well, we put in those things and we evaluate. Which is maybe realize your calculator has these. Your calculator should have the inverse hyperbolic functions in them. Yeah, so they should be in your calculator. If you've got a TI-89, if you got a TI-89, they definitely are there. Probably the easiest way to find them is to go to catalog. Right? And in catalog, it's got, the list of everything alphabetically. And like, I'm down here in the C's. You probably can't see on there. Yeah, no, it's not going to focus. But it's got cosine inverse, and then it's got cosh inverse. All right, so it does have all of those. I think you can also find it on the 89 if you go to the math menu, which is on the 5 button. Yeah, there they are. They're down under a list called hyperbolic, and it's got sinh, cosh, tanh, cosecant, sech, coth, and then all of the inverses. Okay, so they definitely should be on there. Things like Desmos knows these things. So should like Symbolab and all the other online resources and love. All right. Anyway, so if you want to know the cosh inverse of 12, you can actually calculate those out. Also, like if you use the TI-89, you use the integral command with the bounds, it'll just spit out the answer for you anyway. It might actually give it to you in terms of E. Sometimes these things will return it with the exponential forms, but regardless, your technology can handle it. All right, so we did a little bit of algebra to get us to a point where we could do a U substitution, which brought us to an inverse trig. All right, so let me show you another one. That leads to a different inverse trig. But let's say we want to integrate this guy. We want to find the integral of x over 1 minus x to the 4th. And honestly, this integral doesn't look that horrible, right? it doesn't look like it's some crazy weird function that's going to come out of nowhere that we might need to integrate. So I definitely want to point that out, that we're getting these horrible weird functions, these inverse hyperbolics, but they're coming from relatively nice, normal looking functions. That's just how this plays out. All right, so this one, if you kind of think about the inverse hyperbolics, we don't have any square roots, which should lead us to inverse tanh and inverse coth. Both of those forms just had 1 minus something squared. So that definitely suggests a substitution here of about u equaling x squared. Because then we're going to get 1 minus u squared, which is the good form. du is 2x dx. You notice we've got the x and the dx. So if we change it using this substitution, this is now going to look like the integral of 1/2 du over 1 minus u squared. The 1/2 came from the du. All right, well, this is exactly the form for inverse tanh or inverse coth, depending. But again, the default to inverse tanh. All right, well, substitute back in the u. And we end up with this is equal to 1/2 inverse tanh of x squared plus c. So a seemingly nice function, nice-ish function, led to inverse tanh. All right, so there's that guy. All right, so basically what I just did is I threw a whole bunch of new functions at you. These inverse hyperbolics that are defined just like the trigs, just using a hyperbola instead of a circle. Okay, whatever. They also then have inverse functions, and it's all of their derivatives that are actually the important guys for kind of what we've been doing, right? Think about where we are in calculus right now. We're learning how to integrate. We're learning how to, given this function, let's find antiderivatives, plug in the bounds. Right? We're learning how to integrate. In the course of doing that, we're going to have functions we need to integrate that give us these suckers. All right, so think of this as just yet another technique of integration. It's a, here are some more forms to do the integrals. Just so you know, memorizing all this stuff's hard, right? And there are like tons and tons and tons of forms for integrals, for things that we want to look for to integrate. I'm not expecting like crazy miracles, right? Plus, you guys are already taking these tests at home, so I know you've got your notes and all that. But start getting comfortable with these hyperbolics. All right, you don't really need to know where they come from. I think it's cool, but you don't need to know that, but you need to get comfortable with how they relate to each other. All right, because that's what we're going to need going forward. All right, so there you go. inverse hyperbolics and their derivatives. All right, so yeah, we're definitely out of time today. So where we're going, just to be aware, we are going to start doing more techniques of integration. How do we deal with things like, for example, the product rule? We still haven't even talked about what do you do if you have multiplication in an integral. Heaven forbid, what if you have division, right? So we're going to talk about all kinds of other techniques of integration. And that's kind of how this class is going to play out from here on out. Is going to be, we're going to learn more techniques. And we're going to apply those new techniques to things we've already done. So on Wednesday, I'm going to start with integration by parts is the technique we're going to do. Other than that, don't forget, there is homework due tonight. A couple of sections, I think 3 sections that are due tonight by midnight. So make sure you get in and do those. But other than that, I hope you guys have an awesome couple of days, and I'll see you all on Wednesday.